Hi, it's Andreas Stocco here from the Software Institute at USI, Switzerland. In this video, I will present you our ongoing research on predicting misbehaviors in DNN-based self-driving cars. This work is part of Preprime, an ERC advanced grant on testing machine learning-based systems led by Professor Paolo Tonella. There is also a number of people I would like to thank, specifically Michael Weiss, who is a great PhD student at our university, and Marco Calzana, who did his master thesis within our group. The technology we are witnessing behind self-driving cars has matured to the point that advanced driver assistance systems, such as automatic lane keeping, are standard on a number of vehicles. However, developers who have to test the reliability of these systems are undertaking unprecedented challenges. In a very simplified scenario, testing a DNN that performs the task of driving is done as follows. First, human drivers drive camera-equipped cars and record driving data. Particularly, each front image seen by the car is associated with the steering, angle, brake commands by the human driver. All these data are then used to train a neural network that imitates the behavior of the driver. Once the model is trained, it is further tested on simulation platforms until a certain adequacy criteria is met. Then the model is deployed on a real car and is further tested in the field. So in this research, we explore some of the challenges that await developers who are attempting to qualify fully autonomous vehicles for large-scale deployment, particularly devising a technique to perform online misbehavior prediction. But what is misbehavior for this kind of software? Well, misbehaviors can be defined in many ways and are necessarily domain-specific. For lane keeping component, a misbehavior is defined as the car going off-road. There is, however, another aspect which makes this problem particularly challenging I'd like to emphasize. Suppose this input image is given to the car and that the DNN outputs this steering angle. Regardless the fact that the input is known or unseen, the DNN will make a prediction. In practice, we cannot assess the reliability of a DNN-based autonomous driving system if we study the model in isolation, because we need to observe whether the causal effects of wrong predictions on the driving quality, and that can be done only in field, or more conveniently through a simulation platforms, and the result will be as valid as the simulation platform is capable of reproducing the real world with high fidelity. So in the context of our research, we use the Udacity simulator for self-driving cars, which allows to conveniently connect a deep neural network that imitates the driving behavior. So the main limitation of this kind of software is that it is virtually impossible to account for all driving conditions at training time. Therefore, there will always be that one situation that is unknown and that might cause the car to misbehave. The first contribution of this research is that we modified the original Udacity simulator to inject adverse weather conditions such as snow, mist, and rain in a controllable way. For the weather effects, particularly, we used Unity game objects called particle systems. Another important component is an automated crash detection mechanism that records the status of the car. In this way, for each simulation, we can have a labeled data set in which for each frame, we know whether the car is on or off-road. Now we'll show you the same self-driving car as before, driving in such unexpected conditions. The video is accelerated for demo purposes, but essentially we can see that the reliability of the car in the driving task has dropped substantially. Here, one more crash. So the objective of this research is to try predict whether a car is facing an unsupported scenario before the actual misbehavior is observed. In the software engineering literature, we are aware of only one approach that targets a similar problem, which is the input validation strategy of the Deep Road paper. However, their approach was used to identify single underrepresented images in the training set, whereas our proposal is an online misbehavior predictor. Our main approach revolves around monitoring the unexpectedness of the driving scenario and set the threshold to determine when the unexpectedness is raising over an acceptable level. In practice, our approach consists in a redundant component that analyzes the data fed to the car and warns the system if appropriate. In the face of a potentially dangerous situation, the driver might be expected to override the main driving component and recover to a safe state. This architectural pattern can be especially advantageous if the monitor can be made substantially simpler than the actuator. And anyone who has driven for a long time is likely to have stories to tell of freak events they've seen on the road. So imagine a large fleet of vehicles that will be likely to experience all such type of events and perhaps more. And the combination of adverse events and driving conditions that can occur in the real world are simply too numerous to be enumerated and addressed in a classical written requirement specification. So for this reason, we need an architecture that is flexible, that is fast at making predictions, and then can be trained with the largest amount of data available. For this reason, the core component of our technique is based on autoencoders. Autoencoders are neural networks that are capable of reconstructing the inputs they are given with high fidelity. So the rationale using autoencoders for anomaly detection is that the misbehavior predictor will be able to reconstruct well inputs similar to the ones it was trained with, whereas it will fail to reconstruct inputs that are unknown, hence potentially unsupported by the car. We studied different autoencoders architectures in our proposal and compared it with the input validation strategy of the deep road, which is based on a combination of feature extraction and distance in a latent space produced by PCA. However, predicting these behaviors during the motion of the vehicle makes dataset analysis in autonomous driving research more challenging than just identifying single underrepresented images in a training set. To face this challenge, our approach, which is called self-oracle, combines anomaly detection, probability distribution fitting, and threshold estimation into a reconstruction-based anomaly detector with a predictive model of normality based on time series analysis. Time series analysis allows moving out individual spikes that can cause erroneous warnings. Let's now have a quick overview of the experimental study and the main results. Our experimental setting consists of different tracks and weather conditions. We use the sunny condition as nominal and studied the effectiveness of our misbehavior predictor in recognizing when the car is facing unseen conditions such as snow that ultimately led our self-driving car models to crash or to go out of track several hundreds times. So the main research question revolves around the effectiveness of our techniques. And in brief, our results show that our autoencoder-based approach is more effective at predicting misbehavior than deep roads, with a factor of 3 over this existing technique, when the ratio of accepted false positives is set to 5%. Another noticeable results is that the core misbehavior predictions are made up to 6 seconds in advance. So there is, let's say, quite some reaction time for even the driver or another component to intervene and trigger self-healing mechanisms. So to conclude this overview, I presented like a new technique to perform online misbehavior prediction for autonomous driving systems, which is called self-oracle and is promising. If you want to know more, feel free to read our paper and download our tool and simulation platform. Thank you for your attention.